Hey guys, it's Katya, and today I'll be talking to you about Chapter 15, which is also the probability rules. While reading this chapter, please keep these objectives in mind. That you must understand the concept of independence, understand the general addition rule and how and when to use it, know how to find the probability for compounded events, know how and when to apply the general multiplication rule, and how to use tree diagrams and two-way tables. This slide right here is set up with each topic listed, and if you click each one, you will get a little bit of information on separate slides. So if you need help with any one specific topic, please feel free to use these as they are hyperlinked to the slides ahead. Although they are not set up in this video, as you have seen, on the left side will be links to videos from an actual statistics teacher talking about this lesson, and on the right side will be our own personal videos to you guys about your homework, quizzes, and AP questions that involve this chapter. This page right here is set up for links. If you need a little bit of extra help after using this slideshow, please feel free to use them to get a better understanding. The general addition rule. We add the probabilities of two events and then subtract out the probability of their intersection. This approach gives us the general addition rule, which does not require disjoint events. The formula is the probability of A plus the probability of B minus the probability of A and B intersecting. When we want the probability of an event from a conditional distribution, we write the probability of B given A. A probability that takes into account a given condition, such as this one, is called a conditional probability. To find the probability of event B given the event A, we restrict our attention to the outcome in A. We then find in what fraction those outcomes B is also occurred. The formula is written here, and for example, please click here. Police report that 78% of drivers stop on suspicion of drunk driving are given a breath test, 36% a blood test, and 22 are given both. What is the probability that a randomly selected DWI suspect is given a test? Using the additional rule, this is what it will look like. The general multiplication rule. The formula is the probability of A times the probability of B. The general multiplication rule for compounded events does not require the events to be independent, so we can write that it's the probability of A times the probability of B given A. The probability that two events, both A and B, occur is the probability that event A occurs multiplied by the probability that event B also occurs by the probability that event B occurs given that event A has occurred. Independence. When the outcome of one event does not influence the probability of the other, these events are considered independent. When events A and B are independent, we can write the probability of B for the probability of B given A as the probability of A times the probability of B. If you would like an example, please click here. Independence example. A survey states that 56% of college students live on campus, 62 have campus meal programs, and 42 do both. Are living on campus and having a meal program independent? L will represent the students living on campus, M will be the students who have a meal program. Those two together is 42 divided by 56, which gives you 75% or 0.75. Because 0.75 is not equal to 0.62, the events are not independent. Students who live on campus are most likely to have meal plans. This slide will talk about how independent does not equal disjoint. Consider the two disjointed events. Number one, you get an A in this course, and number two, you get a B in this course. They're disjoint because they have no outcomes in common. You cannot get an A and a B in the same course. Tables and conditional probability. One of the easiest ways to think about conditional probabilities is with contingency tables. You can often contrast a simple table to correspond to the probabilities. Whether a Venn diagram or a table is better to use will depend on what you are given and the question being asked. This slide is about drawing without replacement. Room draw is a process for assigning dormitory rooms for college students who live on campus. When students have equal priority, they are randomly assigned to currently available rooms. The example is that you and your friend are up to draw. There are 12 rooms left, 3 in gold hall, 4 in silver, and 5 in wood. You draw first, then your friend. You both would like to get into a room in gold hall. What are your chances that both you and your friend are in gold? When you go first, your chance is 3 out of 12 of receiving gold. When your friend draws, they only have a 2 out of 11 chance. When you write it, it will be the probability of friend draws gold given that you draw gold, equaling 2 out of 11 chances. The reason why we changed the denominator from 12 to 11 is because we are drawing without replacement. Once you draw one, it does not go back into the pool. This slide is about tree diagrams. They show a sequence of events like those we had in the room draw as paths that look like branches of a tree. For an example, you can click here. According to a Harvard study, 44% of college students engage in binge drinking, 37 drink moderately, and 19 don't drink at all. Another way to show that is with a tree diagram. As seen down here, each one has its own separate branch, and we can see in the diagram that it has 3 outcomes, and each one indicates their respective probabilities. Bayes' rule. A tree is often a convenient way of finding these probabilities. It can work when we have more than 2 possible outcomes. When we have the probability of A given B, but we want the reverse probability of B given A, we need to find the probability of A and B intersecting and the probability of A. The result is the formula known as Bayes' rule. Bayes' rule is just a formula for reversing the probability from a conditional probability that you were originally given, the same feat we accomplished with our tree diagram.